So I felt compelled to make this video because Ken Wheeler makes a lot of videos and he repeats himself a lot in the videos, and sometimes he says things or repeats things over and over again that just aren't true or that just aren't accurate or correct. And so I'm a little OCD and I feel compelled to correct people when I believe they're saying something that's not correct. So the other thing I want to do here is I just want to, sometimes people can be not polite. And, Ken can also be not polite. He often refers to Albert Einstein as an idiot and makes fun of Richard Feynman. And truthfully, I don't think it's wise to speak ill of the dead. But that's just me. But the scientific community has really lost their ability to be polite. Back in the day, back when Albert Einstein, was alive and, working with other people, these people were polite. They would write letters to each other. Dear Albert Einstein, I read your paper. And although, I agree with this and that, and I don't agree with this and that. So people were much more polite back in the day, and that art has been lost a little bit. So I'm going to try to inject a little politeness, even though I am calling Ken Wheeler on some of the things he's saying. I'm going to do it in the nicest, most polite way that I can. So, dear Ken Wheeler, as you may know, I have studied your book, Uncovering the Missing Secrets of Magnetism, and have been following your video series for quite some time. In fact, your book and video series were the reasons I started my video series, Understanding Ken Wheeler's Missing Secrets of Magnetism. Although we're on the same page about a lot of things, I am at odds with a couple of things that you keep claiming in your videos, and I feel a need to address them. So here is the more recent video where you make these claims. Nature's Secret of Magnetism, published on April 14th, 2020. And so I am going to play one of the little clip from this video, and then we can talk about it.
Let me give you a perfect analogy, and this is destructive to the supercell. It uses really powerful N60 Gauss magnet. People don't understand that actually a more powerful magnet actually has a smaller spatial magnetic field. The reason being, and the only kind of good analogy I could come up with where people would understand it in their brains is that when you amp up one thing, you also amp up another. So you can't actually make a more powerful magnet without creating a more powerful dielectric field. And by creating a more powerful dielectric field, and this is kind of like the cheap man's version of a black hole, is literally the center black portion will be huge on this really, really powerful N60 Gauss neodymium iron boron. Also, too, the spatial field is smaller. This is why people buy really powerful magnets. They say, I don't understand. I bought a really powerful magnet, and I think I got screwed because the spatial field around it. In other words, you have to get a lot closer to a piece of metal to feel the quote-unquote attraction. And by the way, there's no such thing as magnetic attraction. It's dielectric acceleration.
Okay. So, in this video clip, you claim that a more powerful magnet has a smaller spatial field. In other words, you have to get a lot closer to a piece of metal to feel the attraction. This is what you're claiming in this video clip. So, to test your hypothesis, I bought two neodymium magnets with exactly the same shape and dimensions. One was an N42 grade, and the other was an N52 grade. I did a few experiments and got some surprising results that appear to be contrary to what you said in the video clip. So as many people that watch my videos know, I do a lot of my own experiments, and so I have a new saying, experimentation trumps conversation. And so if you're going to make a claim, at least if you're going to make a claim to me, I'm going to say, show me the experiment. So the first experiment that was surprising to me was that I used the Hall sensor to take a surface reading of the south pole of the magnet using the Hall sensor that I used in my other experiments, and discovered that both the N52 and the N42 had a minus 1.44 reading on the surface. So at least at the surface of the magnet, as I measured all my magnets have a minus 1.44 voltage reading. At the strongest reading is minus 1.44 at the surface of the magnet. So there's the N42 and there's the N52, and they have the same identical reading. So maybe that's not too surprising. But this is a little more surprising. What I found was that, so away from the magnet, I measured the minus 0.03 reading, or just an 0.03 reading. So I measured away from the magnet and got an 0.03 reading here with the N42 magnet. And then I did the same with the N52 magnet and found that the 0.03 reading was in exactly the same spot. So, so that was really interesting. So it seems that the distance of at least this Hall sensor reading for an 0.03 reading with the Hall sensor occurs at exactly the same location. And so I did another experiment where I'm going to, instead of looking for the 0.03, I'm going to look for the 0 measurement. So that's where the voltage drops off to 0. So let's have a look here. I have a specific protocol I use where I, get a reading at the magnet, and then I slowly move away from the magnet to find that reading. And so when this drops off to 0, what I did was I marked that location. And then I tried it again just to make sure. And as soon as this turns to 0, I'm at my exact same spot. Okay, so now I'm going to do the same thing with the N52. So I place this magnet in exactly the same location as where the N42 was placed, and I'm doing my surface measurement, and then I go away from the magnet until this drops off to 0.00, and boom, at exactly the same. I'm going to play that again so you can see at exactly the same location, this little dot that I put from the previous video, it ends up there. So now it's going down, 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 and 0. So as soon as I hit this spot here, this turns to 0. So it seems like the drop-off point, the voltage drop-off point, is in the same location for both the N42 and the N52 magnet. Okay, so now, so one of the claims that you make, Ken Wheeler, is that a more powerful magnet has a smaller spatial footprint. In other words, you have to get a lot closer to a piece of metal to feel the attraction. Okay, so in this experiment, I took a piece of metal, which is a ball bearing, and what I did was I tried to find the distance from the magnet where this ball bearing was no longer attracted. And so because of gravity and the friction of the paper, there's a very specific location where the ball bearing is no longer flying towards the magnet. And that's the location right there. So what I do is I mark that location. And then, so I showed just by touching the magnet, it starts to fly towards the magnet. And so I can place it there, but I can't place it any closer to the magnet. That's as close as I can get. Okay, I'm going to trying it one more time. There, I can stop the magnet there. And as soon as I touch it, it goes towards the magnet. And so that's with the N42. So now I'm going to do the same thing. So there's the point that I marked before. Now I'm going to try the same. You see, I'm moving back and forth just to show you that the magnet is still attracted to, the ball bearing is still attracted to the magnet until I get to this point. And then I can drop the ball bearing without it flying towards the magnet. As soon as I touch it, even a teensy weensy bit, it starts flying towards the magnet. And so I'm doing it again, and just at that exact spot, I can drop the ball bearing there and it doesn't fly towards the magnet until I just touch it a tiny bit. Then it starts to go towards the magnet. So this kind of debunks the idea or the statement or the claim that a stronger magnet, you have to get in closer to a stronger magnet in order to feel the attraction of the magnet. If that was true, then I would be able to bring this ball bearing in a little bit closer to this magnet before, and it should stay there. And it doesn't. The sweet spot for the N42 and the N52 is exactly the same spot. And so this claim that, let me read it again just so we're clear, that in other words, you have to get a lot closer to a piece of metal to feel the attraction, and or a piece of metal has to get closer to the magnet to feel the attraction, doesn't appear to be true. Okay, so here is just a snapshot of that experiment, and you can see that the distance from the surface of the magnet to this sweet spot is the same for both the N42 and the N52 magnet. And this is an experiment anyone can do, anyone can order. The magnet is 1 inch in diameter and 1 inch high, 1 inch in diameter, 1 inch high. Anyone can go and buy 2 magnets, N42 and N52, and repeat this experiment. It's not rocket science. Okay, so I checked the K and J magnetics, and just to see if I can get any clues as to, why this might be so. And so here they're talking about the surface field. So I'm assuming they're talking about the surface measurement. And they said the surface field is the strength of the magnetic field measured right at the surface of the magnet, just like I was doing with my Hall sensor. It's the field strength you might measure if you could squish it, whatever. The number depends on the magnet material. Okay, so the field strength at the surface of the magnet depends on the material that the magnet is made up of, the shape of the magnet, and how it is used in a magnetic circuit, which would be the Hall sensor. So the surface field strength really has nothing to do with the grade of the magnet, the N52 or N42 number. It seems to only depend on the material and the shape and size of the magnet. And this is what I'm seeing. And so, but this also seems to be true at a distance, not just on the surface. Okay? So, so I'm going to play this clip. This is the second clip that
See how huge the black hole is, or the black section of the dielectric portal is on this powerful magnet. And also, too, you could see, if I can get a little bit better focus, the concentric circles. You actually see shades. It goes from black to dark red to orange to lighter orange to almost yellow. This is the magnet that will very quickly. Also, too, you can see these bright points right here. You see that? You see how quickly it's destroying the cell? This is what I mean by burn-in.
Okay, so basically what you are saying here is that the stronger magnet is going to have a stronger dielectric signal. And in fact, this is what I see. So this is actually correct. This is what you're saying in this part of the video is actually correct. When I put the N42 magnet under the ferrocell, I get a much softer black hole region. If you want to call it a black hole, I don't mind. This black region is not as dark as the N52. The N52, you see a very strong dielectric signal here. You see a very strong black hole region, and you see, you know, some colorization going on here. There's definitely a difference between the N42 and N52 when you look at it under the ferrocell. So this part of the video where Ken talks about that is 100% correct. I have no problem with this. This is fantastic. This was actually, up until today, this was the only way I could tell the difference between the N42 and N52 magnet. Now today, I got the idea to test the magnets with the CRT screen. Okay, so what I did was I put a little piece of tape on the screen so I could put the magnet in exactly the same location. And so I took the N42 and placed it on the screen and took a picture. And then I took the N52 and did the same thing, placed it in the exact same location, and you can see when I flip back and forth between the N42 and the N52, you can see that there's two things actually. First, you can see that the black void is a little bit bigger for the N52. Okay, N42, N52, N42 is a little smaller, N52 it's a little bigger. And also you can see that this, these I don't know, field lines, if you want to call it, are actually expanding for the N52. So let me flip back and forth, and you can see that the red is a little bit closer to the magnet in the N42 and a little further away with the N52. And the other thing I noticed was in here and in here. So this region here changes a little bit when I place the N52. What happens is you've got the colorization here is like blue, green, red, blue, and then here it's red, blue, green, red, blue. So the red is coming in. It's not there with the N42, but it's there with the N52. And if you look down here, you see a similar thing. With the N42, you have the green, but then with the N52, you've got the blue preceding the green. So the green gets shifted out here, and now the blue is coming in. Here the blue is getting shifted out, and now some red is coming in. So in this case, the N52, see, the whatever you want to call this, I'm not sure what to call this. This is not the field, but whatever this is, it's actually expanding for the N52. So yeah, and so that is that for the field strength. Now there's another thing that Ken talks about in this video, and I'm just going to play the clip, and then I will talk about it in a minute.
Now, of course, you can see the donut shape. There's nothing here, by the way. This is not a projection device. This is literally just LEDs, like for the edge lighting of your cabinet. So there's just light shining inwards. By the way, about 2 years ago, people said, well, you're just looking at the number of lights here. It's like, that's not true. I created one of these devices where the light pours in from the sun, so only one light source. So the sun was able to wrap around in a tent-like structure and shoot inwards into the cell, and you get the exact same thing from a single light source, which is the sun. No batteries, no LEDs, nothing, just the sun powering it. Now,
okay, so I did a similar experiment where instead of using sunlight, I bought a continuous LED strip. So this was continuous lighting rather than the discrete LED lighting. And what I found, was that I didn't get the hypertrochoid pattern with the continuous lighting. The continuous lighting gives a more continuous effect, and of course, actually, let's just have a look at. my little video clip here. So you can see as I move the Ferrocell around, you're seeing continuous lighting. You're not seeing the hypertrochoid pattern, and you're seeing the black hole, which I make an analogy with the black hole image that was taken last year. So that's why I put these side by side, because I thought this reminded me a lot of the black hole. But the point of this video is to show, like with the black hole image, you don't have the hypertrochoid pattern. And with my continuous lighting system, I don't have the hypertrochoid pattern. And so I think it's not true what Ken is saying, that when you have a ferrocell with 36 lights, you've got 36 lines. It is directly related to the LED lights around. It is not constructive and destructive interference, because if that was true, then I would see it in this image. And in fact, the ferrocell that I'm using in this video is actually one that Ken Wheeler gave me, so it's actually quite a good one. I kind of started to leak out a bit here, so some of the fluid leaked out, but I'm still able to use it to get a really nice image here. And so I don't think this is correct what he's saying. I wasn't able to find the video with the normal lighting or the sun lighting. But definitely I'm not seeing the hypertrochoid pattern here. This is continuous lighting all the way around, and this is what I'm seeing. Okay, so in conclusion, it appears that some of the things that you are saying, Ken, in your videos are incorrect, especially regarding the spatial reach of the stronger magnet and regarding the display of the ferrocell under continuous lighting conditions. You may want to consider repeating the experiments that I did to prove to yourself that what I'm saying is accurate and correct, and then transmit that information to your audience so that they can be better informed. Sincerely, Fractal Woman.